All right, I think I'm ready to start. Hi, everyone. Thank you so much for being here. My apologies for not being able to make it in person there, but I would have loved to be there. It's just the visa stamping issues and the delays and everything, thanks to all the travel things that are happening right now. But here I am. I'm Tarika Chawla, a senior mobile application security engineer at Shopify. Today, I'm here to talk about different security aspects that we should keep in mind while we are making an Android app. So, just to start with, Android security feels a lot more like a moat. Moat is a deep ditch filled with the water, which is around the castle. And usually, this castle has like one entrance on the front and one exit or an entrance on the back. So clearly, the only two security points that this castle would need is at the entry point, at the exit point, right? Sometimes Android can feel a lot more like this kind of moat where the unlock screen is the only place where you would need the security, right? So this is how we assume that the security needs to be at the unlock screen. Whereas the important thing is, it feels a lot more like the Android security is a lot more like this, with multiple doors on multiple different doors, which is basically multiple different code bases or different features where you would need multiple different kind of locks that you would need to put in order to make it secure. It's the same if you think about it, like why do you need all these different locks, right? You can think about it with the bike analogy too. Let's just say that on a bike stand you have different bikes with different kind of locks. Some have weaker locks, some have stronger locks. And guess which bike would go first? Well, in a real situation, probably the tires would go or the seat would go. But in a very hypothetical situation, the thing is that the bike with the weaker locks would be the one to go first. So we can think about it in the same way when our app is right out there and on the Play Store once you release it, right? Hackers would come for a window shopping and they would want to see which app is easier to hack around with, or to just kind of break it apart and then see which is more vulnerable. So the best we can do is make our app secure than other apps on the Play Store. So with our team at Shopify, we were able to come up with the list of locks that you can put on your app, in your code base or in the device, to make sure that your apps are secure in general. And this is like the basic line of security that you can add. So let's start with storing sensitive data. There are different places where we store the sensitive data. Let's start with the apps first of all. In the app, there are multiple places where you would store the data. The first one is shared preferences. Usually shared preferences is the first one that we use in order to exchange data between the activities or other things, but within the app. But when it comes to sensitive data, make sure that you're using encrypted shared preferences. Encrypted shared preferences class is available in the Android X security module. It works exactly the same way as as shared preferences would work, just encrypted. It's just another module. So whenever you're trying to save sensitive data, make sure it's in an encrypted shared preferences. The other way that we save data in our app is through content providers. The most important thing in the content providers is Android exported is equal to false. Usually when you would add this content provider's intent in your Android manifest file, somehow the Android exported true might just come in the copy paste that you made, or it might not even be there at all. So you have to make sure that Android exported is equal to false in most of the scenario. In fact, having Android exported is equal to true is a red flag. Doesn't matter in the content providers or anywhere else in your Android manifest file. Why is that? Android exported is equal to true makes it a default thing that anything outside your app can trigger that. Let's just say it's a broadcast receiver, right? And it has the Android exported is equal to true. Then anything outside your app should be able to trigger it just because you have the Android exported is equal to true. So make sure that if you put that Boolean as a true, You need to have a very solid reason and mandatorily that you need it. But otherwise, make it false for every single intent in your Android manifest file. Now let's talk about the sensitive data that you have in your code base. So what if you have secret keys or even just a vulnerable logic that you thought that, oh, I'm going to compile this app into an APK and ship it out there and nobody is going to see it. It's a vulnerable logic, but only I know. Well, guess what? Decompiling your app is as easy as removing a DRM from an ebook. It just needs a software. It's zero effort. So in order to protect your code base, the code that you have written, we have ProGuard. ProGuard is a lock. It's still a weaker lock because what ProGuard does is that it will shrink your code, but then eventually someone can go and decompile it as well. And it just takes longer to decompile it. But with ProGuard, it's still a better lock than a no lock. So what does a ProGuard do? The first thing is it shrinks the code. Then it also shrinks the resources that you have in your Android code base, and then it obfuscates the code itself as well. What it also does is it also optimizes your code in order to, and also reduce the size of your app's text files. In fact, it also optimizes your code in a way where, like, let's just say that if you have an if and else statement, right? And according to the logic, the stuff, like the code that is in the else statement, you're never going to reach that. It's going to remove that altogether because it knows that it'll never reach that else branch. So this way, it'll be able to reduce the app size as well, shrink your code. So what that does is that basically makes it harder for any hacker to decompile your app. It's just not a software effort anymore. They'll have to go from at least 3 barriers are better than a 1 barrier. It's literally just that situation. So for that, you have to make sure that you enable ProGuard. The disclaimer I would have is if you it depends on the infrastructure. Like in case of Shopify, ProGuard becomes counterproductive because we have a bug bounty program where on HackerOne we give hackers a chance to go through our app and report the bugs that they find, any kind of vulnerabilities that they find. So for us, we will be just like making their work harder for no point. So for us, having ProGuard doesn't make sense. But if you do not have this kind of infrastructure in place, then the recommendation would be to enable ProGuard. As I said, even if it's a weaker lock, it's a better lock than having no lock at all. That being said, as I said that with ProGuard, it definitely delays the decompiling and processing your code, but it is not impossible. Having said that, let's just say that if you have a secret key in your code base, the hacker will eventually see it. So the most important thing is you do not have the secret keys in your app code base at all. Because eventually, if they're able to process your code after the ProGuard and gotten to a point where they can see your entire code base, they will be able to find the secret keys. And that's usually the most easiest and the first step to hack any services, right? So basically make sure that you have ProGuard enabled and you do not have any secret keys in your code base. Moving on to the next thing for the sensitive data in the devices. Till now, we have talked about sensitive data you're storing in your app. Then we talked about sensitive data being stored in your app code base. Now we're going to talk about the sensitive data in your devices. So I'm sure you all have worked with the key generator, key pair in order to create the public-private keys for the RSA public-private keys in order to add an encryption logic in your code base, right? In that case, if you have noticed that if the RSA public key is always sent to your server or somewhere that with whom you need to have this encryption relationship. But the RSA private key, that gets saved in your device. What that means is that it is our responsibility to secure that device and make sure that it is secure. For that, Google has created certain kind of locks for us. So you know how bike manufacturers have created locks, but it's our responsibility to put those locks on the bikes to make sure that nobody steals them, and in fact not to leave the key in the lock as well. That's also our responsibility, right? So same goes for these locks as well. You have to make sure that you put these locks in place in order to secure your app. So coming back to storing sensitive data in the device, Google has created this hardware security module, HSM, which basically makes sure that it provides better security features for your device itself. Hardware security module includes Strongbox. Strongbox provides better security measures for against physical and side channel attacks. What this hardware security module is, it's its own operating system. So think about it, Android as a platform, and you have a main operating system where all the apps work, and then you have HSM, which is basically its own operating system. Both the operating systems tend to communicate with each other through a restricted interface. This restricted interface is basically just a shared memory region where they put the data and then use that data, like basically exchange the data. The important thing to know is that if ever the Android operating system gets hacked or gets compromised, the HSM system, the operating system, would not get compromised. So basically, even if your device is compromised, the data that's being stored in this hardware security module using the Strongbox would not get compromised. So the very first thing is that you basically check on your, whenever you're creating these kind of public and private keys, is that whether your device supports the Strongbox. If it doesn't support the Strongbox, it definitely has this trusted execution environment, TEE, on your device. So if you don't have Strongbox, you check for TEE. If it doesn't even have TEE on that device, then the last and the foremost thing is you make sure that they have a lock screen enabled on their phone, because that's like the last line of defense that you can have. So Strongbox versus TEE, Strongbox is highly recommended. It's definitely a lot more secure. The only disclaimer that comes with that is that Strongbox is definitely slower than TEE because it has a lot more fewer concurrent, because it is resource restrained, hence it only has very fewer concurrent threads that run at a time. Whereas TEE in that case is a little faster, but then it's a little less secure than Strongbox. So if you have Strongbox in the device, then you go with that. Unless it doesn't have Strongbox, then you come back to TEE. We will talk about how you can enable or make sure that Strongbox is being used to store all this sensitive data on the device. Now let's talk about permissions. Let me just move this here. So the permissions that we need in our apps, first thing I would say is that if you have to make sure that you actually do need those permissions, right? Like, why would you ask for random permissions if you don't need them in your app? Depends on the features, right? But the best you can do if you do actually need that feature is to defer the permissions. What do I mean by deferring the permissions? So let's take an example that you have a feature in your app where you have contacts, basically where you can message someone right in your app, or you can call someone right through your app or something. And you also want to add on top, be able to add more contacts, in your app. So in that case, you would need a write contacts permission from your Android manifest file. But what if any other app already has that kind of permission? The contacts app, right? Like it already has that write contacts permission in the Android manifest file. Like basically they can already do the job that you're planning to do. This does two things. First, the users are already used to adding the contacts through their contacts app. What this would do is it'll create familiarity and consistency for the users to be able to create more or add more contacts. So basically what your app does is it eventually defer the action and the action to the contacts app to be able to add the contacts. Instead of you adding that feature, you simply send them to the contacts app to add this intent. The second thing is, this was us talking about taking permissions to use the resources in the device. Next is taking permission or finding a way to how to give access to users sensitive information which is in your app. Let's take an example that in your app you have a bank account information available for your users to see. In order to give them access to see that kind of information, you should have a PIN or a biometric authentication in place in order to even give them access to see that information. This creates a barrier even for the user, and it also creates a security feature for the users in case they have lost their device, or in case they even had the app open and somebody had access to that app, like for even for a couple seconds, right? And they're trying to access their bank account information, but then it requires their biometric authentication. Boom, your app is a lot more secure, right? um, but there are certain places where you might need a lot more re-authentication than just a biometric authentication for certain kind of sensitive actions, such as account deletion, or even just changing credit card information on the app. You should have a proper user re-authentication where you basically take them back to the login page, and then they have to add their credentials, and then you log in, and then you go back to basically initiates that sensitive action for them. For this, your server has to be able to check when this access token itself was generated, as in like how far back did the login. So, and it should be between maybe 2 minutes or 1 minute. So it really depends on how it works with your server and the client. But your server should be able to recognize that the last login that happened, like it's not a fresh login, which means that they won't be able to complete the request. So this way, you should be able to get a user re-authentication for sensitive actions. And you have created better permissions for the safety of your own users in your app. The next is entry and exit points in our apps. Well, according to the mode, the only entry and exit points would be the unlock screen. But that's not the case, because on an operating system, it's its own world, right? And we have multiple apps which do multiple things, and there could be an evil app out there, or that's just trying to hack into other apps. So let's talk about the entry points. There are multiple entry points you can have in your app. Let's start with the deep link activities. So all the URLs, what do I mean by deep link? So all the URLs in your email or coming from any text messages or anything can give access to your users to open that specific link in your app instead of the browser. You just need that deep link inside your URL, which basically says com dot something, and then like basically something very close or like exactly similar to your Android manifest files package name, right? And that will give that's what Chrome recognizes, right? Like it'll basically, when you click on a link, it says, oh yeah, I have an app which is very which is exactly that, or you want to open it in the Chrome browser, right? And then someone might just click the app. What if it's a hacked or a phishing URL, right? Which is trying to get into your app and hack its way up. So in that case, the first and the most important thing you do is that you do not have any deep link URL initiate any action in your app itself. The best way to deal with this is that if there is a deep link, you want to have this deep link flow in your app, you take them to an activity where user can further initiate the action. So basically you click on a URL, it takes you to an activity in your app, and then the user do something like whatever they need to do and initiate an action. A much better way, if you have more time, would be to create a deep link activity. In this deep link activity, you make sure that you sanitize your URL. Basically, regex match the pattern, the basically the path that's in the URL, and based on that, decide which activity needs to go. Like basically, if you have multiple kind of deep link URLs that needs to do different things, right? So a deep link activity would be that place where you check the path, regex match it, and then make sure that okay, it needs to go to this activity. That's the first step. The second step would be for you to match the parameters that are coming in that URL. So let's just say that the URL matched the path, but it didn't match the parameters. But this activity requires these parameters, ABC. But the URL sent you the path exactly to that activity, but they send the parameters which are XYZ. These two things don't match. So in that case, you should have a failure screen in place, because you do not want to send a random deep link URL on your app and do something, right? Next up is the broadcast receivers and services. I already mentioned this with the content providers as well, and I will say it one more time that if you want to have the Android exported is equal to false, well, if you want to have it as true, then there's obviously a different procedure that we follow. But most of the time, if you don't need it, if it's just happened to be there, then make sure the Android exported is equal to is false and not true. If you do want it true and it's mandatory, it's necessary for you, then make sure that you have signature level security enabled. What that means is that any other app out there should be able to trigger it, but only if it's signed with the same exact the keys that you signed this app with. So that's called signature level security measure, which basically means is that let's just say that you have two apps and you want these two apps to talk to each other through a broadcast receiver, then you need to make sure that these two apps are being signed with the exact same AP, same key, basically same signature, same key, and they both are signed with that signature for the APKs that you're releasing. Moving on to next one, notifications. Notifications is yet another way where it works a lot more like a deep link where you click on notification, it takes you to the app. But nowadays, obviously, even within the notifications, we have a way to initiate the action, like accept, decline, or like basically a 2FA method, right? You have it right on the notification through different buttons that you can just press and initiate the action. Great. So the deep link activity kind of method would not work here, right? For that, we have a recommendation where you should have an end-to-end notification encryption. The reason you need an end-to-end encryption is because for a lot of things, one is hopefully any other app is not reading your notifications. Second, any random server is not sending your app the notifications that you are clicking on. So for that, we have the end-to-end notifications. And let's dive further into those notifications. Like how do you manage to have end-to-end encryption? Well, the first step is that we always register the device for the notifications, right? Like the very first step is you generate the device token, and then you send the register call to your server to let them know that, hey, here's the email, here's the device token that you would need to send the notifications. So when you're sending that register call, before you even get to the register call, you need to create the RSA private and public keys. And this is the entire process for how you would create that. The first step is that you create the spec builder, and then you have the RSA key generator parameter spec. So basically, you generate the key pair of public and private key. The important thing in this code base that I want you to notice is spec builder.set is strongbox to true, which is if you're looking at the code and you see the spec builder dot code, look at the last spec builder dot, that is set is strongbox to true. That's how you make sure that the RSA private key that you have is actually being stored in using the strongbox on the device. The one that I was talking about earlier about how to use the HSM module. Once you have created the private key and the public key, what you do is you send the public key in that register call to your server, because they also need that exact same public key to encrypt those notifications. So once they have encrypted the node, so basically, let's just say that you did the register call. Now your server has your email, the device token, and the public key. When the server has to send the notification back to your device, what they need to do is use that public key and do the encryption on that notification and then send the encrypted notification on your device. The next step is, once you have received that encrypted device, how do you decrypt that notification? So first of all, you go back and find your private key using the key entry that you have. So this is the code for extracting your private key that you created in the previous slide. Once you get your private key, you can use that private key to unwrap the IV that you got in that encrypted payload, the notification, and then you also decrypt the AES, the secret key as well. Once you have both the unwrapped IV and then the decrypted AES key, you can go ahead and decrypt the notification that you received from the server. And this is the process for decrypting the notification. So basically, you instantiate the cipher class with the certain kind of padding, and then you instantiate the parameter spec, which because you already have the unwrapped IV key, you just use that, plug it into your parameter spec, and then you start the cipher in it, like basically decrypt, and use the decrypt cipher to finally decrypt your notification. Right, now let's move on to the exit points. The exit points on our apps can be web views, because the moment you load a web view in your app, you're already technically outside of the realm of your app, right? So in that case, so web views is a very vulnerable thing that to use, right? But the problem is that there are a lot of scenarios where that seems like the optimal solution, right? In fact, they work, and they work really good. Like, I can't complain about the web views, right? Like, because they work in the situation where nothing else would work, right? But web views are vulnerable. Well, the first thing is that the tragedy happens when any untrusted code gets rendered in that same web view, right? It could be any random URL, or even the user can just, kind of get lost in that forest of loading different URLs, or like clicking on something, moving on to something else, and then just, lost in their own wild world out there. So in that case, the best that would work is an allow list. What that allow list does is that you can add different domains that you would allow them to be able to load in that web view. So what our web view does is, like, every single time it gets a request to load a certain URL, it goes and checks that allow list. Is it there? If it is, then it'll load that web view. That's the first step, where you can control different kind of domains. Like, let's just say that your web view doesn't only load the load your server domain based URLs. It loads other domain URLs as well. So you need to have that allow list of domains which you would allow, right? So allow list works for that. The next step is that when you have the is JavaScript enabled. So web views in general are really famous for the code injection and cross-site scripting, because obviously, I mean, you're rendering domains which you don't have control over, and you don't know where the user would navigate, right? And then on top of that tragedy, you end up enabling the is JavaScript enabled, which basically means that your web view has the right to render the JavaScript code as well, to run the script that was written in JavaScript in your Android app, right? What that does is that's like the key to code injection, right? You're basically, but you initiated it. You are the one saying that, oh, here's the code that I am injecting. You need to run this on an Android app, right? So you're like, yeah, run the script on this activity, on this web view activity, right? In that case, you have to make sure that is JavaScript enabled is only enabled for the domains that are in your control, as in, every single code that would render on that web view. That is the only reason you would ever have is JavaScript enabled. If you cannot control the domain, if you are not the owner of that domain, then do not have this JavaScript enabled. And then comes the god of everything, add JavaScript interfaces. When you say add JavaScript interfaces, you're already telling your Android is basically, here are a couple of JavaScript interfaces that I want you to run. You already have is JavaScript enabled on that web view. So you're basically giving them the purpose, like basically to, fulfill their evil purpose. So let's just say that web view and had a JavaScript enabled, and it told you, it told like basically the evil code in that script has the code to run all the interfaces that you have added in from through your Android, run those interfaces in a different way, not what you expected, but in an evil way. So that's how you will eventually get into the code injection and the cross-site scripting. So make sure that is JavaScript enabled, and JavaScript interface only happens for the domains that are under your control. You know exactly the code that will be in in those domains, like in those URLs that are being rendered. Next is the network security config file. So this network security config file, why I added in the exit points is because this is, so I'm sure if lots of you have used the Charles proxy in order to look at the look at your calls, and then the response, the request that you send, and the response that came back, right? So in that case, well, the first thing is that you should have this network security config file, because you do not want your release app to be able to get on the Charles proxy. What that means is that a random person can, just take your app and then plug it in with your Android device and then open the Charles proxy and be able to see all the calls that are happening. I mean, really, no, right? You don't want that. So the best way to deal with that is that you add this network security config file, and then you add the debug override in there. What this does is, this network security config file does is, it makes sure that you can only do the Charles proxy while the app is in the debug mode and not in the release mode. So now your Charles proxy would only work with the debug mode when you're working on it, but not in the release version. The other important thing here is the domain config, the very first line, domain config clear text traffic permitted is equal to false. What this does is it makes sure that you're only running, or all the network communication that's happening is HTTPS, so SSL based. Next is recommendations. So we do have a couple of logs that we feel that you should have in your app, in addition to all these different logs that are kind of necessary. So now we're moving on to the recommendations. The first one is OAuth 2.0 with PKCE. So I'm pretty sure, so what is OAuth? I'm pretty sure a lot of us use that to, talk to our servers, like through API calls to get access to the data. So what is this OAuth? OAuth is a secure open protocol which allows us to have a secure authorization with our server in order to get that access token, which we further use in order to get the get the data through the API calls, right? So it's the keyword is getting the access token. That's what OAuth helps us get. So how does OAuth works? OAuth will, in OAuth, the general process is that you would go with the authorization request, which further gives you the authorization grant, which is basically an authorization code. Once you have that authorization code, you take that authorization code and request the server that, oh, here's the grant code. Can you give me the access token? Authorization server knows, yes, that is the correct grant code. I know this. And then it gives you the access token back. Once you have the access token, you can go to any server, the resource server, where you would get the data based on that access token. So basically account information, or like basically anything related to that specific user, because access tokens are specific to specific users. So let's ask a couple of questions to ourselves. So as I mentioned that, once the server knows that, oh yes, this is the grant code, let's just, let's just give them the access token. Well, the first question would be, how does the, I guess, how does the app knows that the request that I sent for the authorization code, or even for the access token, is like I'm getting the access token back from the exact same server. How do we know that I'm not receiving this random access token from a random server, or even though I sent the request to my server, like my server, evil server. So I sent the request for access token to my server, but somehow an evil server responded back. Because there was no check, you assumed that it came from your server, right? Like obviously it came from a phishing server, but how would you know? Well, OAuth has something in place which will help us to recognize whether it came from the server that you initiated the request with or not. That's called, there's a parameter named state in in our request URLs. So basically what state is, it's a random string. So we generate a random string and then we SHA-256 it. Basically we encrypt it, hash it to a basically a hash string, and then we send this state parameter with our request callbacks. So basically, let's just say that I wanted to send a request for an authorization grant. You can see the parameters here. So basically, I sent the state with the hashed version of the random string that I generated to the server. Whenever I do get a response back from this URL for this authorization grant, what I can do is the server has to send me that state parameter back with the exact same value that I sent it. So on the app side, what you can do is you will basically make sure that the state matches for what you sent versus what you received. This way you know that, oh, it's the exact same server that sent it. Let's reverse the question now. What if, how do the server knows that, like, let's just say there are two apps. This is your app, this is a malicious app, and here's the server. Let's just say that basically, you sent the authorization code request and you got the authorization code back. What if this malicious app also has that grant code, and this is the grant code, this is the app that sends the authorization grant code to get the access token back? How do the server knows that it came from the correct app, right? Well, OAuth 2.0 in itself doesn't have the answer to that question. So what happens here is, as I just mentioned, so basically you sent the authorization request to your server, but when the authorization code came back, it went to both the apps, the malicious app and your app. So how do we make sure that it's just your app that receives the access token? So we have something called OAuth 2.0 with PKCE, that's PXE. What PXE does is it basically further adds more parameters into the callbacks or the request call URLs that you're sending, where in the code where basically we'll start with the first step, where app generates a random string, hash that random string. When we're sending a request for an authorization code to our server, we send the code challenge and the code challenge method parameter to our server, which basically the code challenge is basically the base 64 encoded of that hashed code verifier string that we created. So how do you create the code verifier? You have a random string, you hash it. Then comes the code challenge, which is basically the base 64 encoded of that code verifier. What we send to the server is basically this code challenge and the code challenge method. And this is how you send the parameters. So basically the request for the authorization grant, you send the code challenge and then the code challenge method. When you send the request for the access token, like once you've already gotten the grant code, right? Now it's time for you to use that grant code and send it for the access token. Like I want to request the access token, here's the grant code. In that request, you send the code verifier instead. The reason you would send the code verifier this time is so that when it goes to the server as a request, it needs to check on your server side that whether the code challenge and code verifier matched or not by decrypting the code verifier that you sent. So this way, the server knows that it came from the exact app which actually sent me the initial request of the grant code. So the malicious app is out of the picture. The next recommendation that we have is the Play Services Security Provider. What that is, so our Google makes sure that all the network communications that are happening in our Android app are secure. And for that, it has a security provider in that app code base, right? So what Play Services has is it has a way for you. It has a class install provider, which basically makes sure that that security provider is up to date with all the new security patches, and it's basically updated version all the times. There are a couple reasons you should have that private provider class is because, well, the first step that it would take is that it'll basically check whether you are on the updated version or not. Second is it even has functions called install if needed async and install if needed, for you to for Play Services to by default update the version or install the newest version for your app to use in order to have these networks communications. So adding it's a bit tricky to add this the security provider and like make this entire thing work, but it's definitely worth the effort. The last thing that I would like to talk about is the private keys in GitHub. So if you have heard about CodeCov, it's basically a software which helps you understand how much test coverage you have. And the easiest way that it can find the test coverage is by counting the number of lines that were covered in the unit test that you had. So basically how many lines ran in your unit test or in all the tests that were there. And it happens on GitHub, right? Like as you use Circle CI, you have the unit test and you're good to go. The problem is that at some point, by mistake, all the secret keys, like basically all the code base that this CodeCov had got leaked. So basically, hackers had access to all the code bases that CodeCov was using to calculate these number of lines. And the biggest problem happened when people had secret keys in their code base, which were committed to the GitHub, like basically the private keys. I'm pretty sure there are a lot of times where you ended up committing a private key or like a secret key to your GitHub, and then your team members red flagged it and be like, what, we'll have to, switch the private key now because, and especially the prod private keys, right? Development one's still okay, but it's always better. The recommendation in that case is to make sure that you have an eJSON file where you would put these secret keys and encrypt them before you commit them to GitHub. The other reason you might have secret keys, and you usually have them for Circle CI builds. So if you have Circle CI builds enabled or integrated with your GitHub repo, most of the time there are secret keys that your Circle CI would require in order to compile the app together, run it, and like do the proper build, right? So even in that case, you should have an eJSON file in your code base where you would like add those secret keys so they are encrypted. And this way you don't have to go through when this CodeCov vulnerability happened. A lot of teams just went back into their code bases and used Trufflehog to scan through the entire code base. Like basically Trufflehog made it easier. It basically checked which kind of things looked like keys or like private keys or secret keys, and gave us like a big file to like look through, like the text files to look through, and is this a secret key, is it what changing, what rotating or something. So yeah, it can definitely help save a lot of effort if that kind of thing ever happens. So yeah, just gonna wrap up with the outline. So basically we were able to go through storing sensitive data in your apps, in your app code base and your device. Then we talked about permissions, on how to defer those permissions, and then the entry points we have, and then the exit points such as the web view, the network security config file, and then the recommendations about the OAuth 2.0 with the PKCE, the PXE, and then the Play Services security provider, and then the CodeCov. And I think that'll be a wrap. Thank you, everyone. If you have any questions, feel free to connect with me on LinkedIn or Twitter or anywhere. Thank you.